Today we're going to be talking about eigenvectors and eigenvalues, but before going into how to find them, we'll first give some understanding as to why these are a useful concept. And to understand why they're useful, we first need to understand why matrices are useful. And so matrices transform vectors. And so if we have a matrix M given by 1, 2, 2, 1, and we have a vector V given by 1, 3, then we can multiply these two together because they have the correct dimensions. And when we multiply these two together, this will be given by 1 times 1 plus 2 times 3, as this is the rules of how to multiply a matrix and a vector, and it will also be given by 2 times 1 plus 1 times 3. And so if we add up these, this will be 7, 5, which we can call a new vector W. So here we see that we've applied a matrix onto a vector and we've managed to result in another vector. And this can be shown graphically. Here we have a vector 1, 3, which goes along 1 and up 3 units. And upon applying our transformation, we see that this vector rotates and elongates to be 7 units across and 5 up. We can describe these transformations more generally though if we introduce a vector, let's call it A, which has values x and y, where x and y are any real number. We can then apply our matrix to our vector, which if we do this in the exact same way as before, we'll end up with x plus 2y and 2x plus y, and this is our new vector b. So we have now transformed our vector A into a new vector B in terms of its old position. So let's just do a check. If we wanted to transform I hat, let's say, and we know I hat is 1, 0, this is equivalent to letting x equal 1 and y equal 0, which implies that M acting on I hat is going to be equal to, setting these two are 0, these two are 1, is 1, 2. So now we found out how our vector I transforms under the matrix. You can show this generic transformation by considering this grid of vectors here. Our green vector is I hat and our red vector is j hat. Every possible point on this grid, not just the grid lines, represents a possible vector. The transformation then will stretch and deform this original grid, and so we can see that our green vector went from 1, 0 to 1, 2, as we've previously shown it should, and every other point has been stretched and now changed. And from this we can now understand eigenvectors and eigenvalues. Considering the eigenvectors 1, 1 and 1, 2, the whole point of them is that under a transformation these vectors do not rotate, as you can see here. They just scale by a different factor. And this scaling factor, so in the case here we can write this as 3 times our original eigenvector, or minus 1 times our original eigenvector. This scaling factor is known as the eigenvalue, and the vectors that are only scaled by the transformation are known as eigenvectors. Having now seen what eigenvectors are, we will now look at how to find them. And the first thing to do is to solve what's known as the eigenvalue equation, which is given by our matrix times our eigenvector is equal to lambda times our eigenvector. Lambda here is the eigenvalue, and this is simply the description that I gave before of our matrix times our vector is simply equal to a scaling of our original vector. To solve this, we expand out this as so, which we're allowed to do, and you can show these equivalent by expanding this back. We then subtract off this matrix from both sides of the equation. So we end up with 1 minus lambda, 2, 2, 1 minz lambda z is equal to 0, 0, 0, 0 times z. Often written as just 0, which is technically a vector. What we then do is we then take the determinant of both sides of this thing, and the determinant of 1 minus lambda to 1 minus lambda is given by the multiplication of these two subtracted from this multiplied together. So we have 1 minus lambda squared minus 4. And this is equal to the determinant of this matrix, which is obviously 0. So we can expand out this side. We have lambda squared minus 2 lambda plus 1 minus 4 equals 0. And this is simply lambda minus 3 and lambda plus 1, which we should be able to factorize. Now, if we have two terms that are multiplied together to equal 0, we actually have two cases in which this equation is satisfied, and that's when lambda minus 3 equals 0, or when lambda plus 1 equals 0. And so this leads to lambda is either equal to 3 or minus 1, which is what we saw when we pictorially showed the transformation. To find the eigenvectors of the problem, we calculate them in each case for the different eigenvalues. So let's start off with the case for lambda equals 3. In this case, our matrix 1 minus lambda 2, 2, 1 minus lambda times our vector z just becomes the matrix minus 2, 2, 2, minus 2 times z. And if you remember, this matrix times vector was equal to our 0 vector. We can represent this eigenvector as some z with some x and y component. We then expand out this matrix times vector problem, and we're left with minus 2x plus 2y is equal to 0, and we'll get that for both top and bottom. This therefore implies that x is equal to y, and this actually solves the problem even though it may not be clear why. So for example, if we let x equal 1, then we'll have z will be equal to 1, 1. However, you may be thinking, what about if we let z equal to 2? Then is 2, 2 still an eigenvector? And the answer is yes. Eigenvectors are not uniquely defined. So we can show this here. If we multiplied 1 times 2 plus 2 times 2 is equal to 6. And we're also going to get the same for the bottom. And we see that 6 is 3 times the original eigenvector. The reason eigenvectors are not uniquely defined is because all that they must do is lie on the line that we have shown is not transformed by our matrix. Our line is given by the equation x equals y. And it means that any vector that is along that line and points on it is an eigenvector. So even something like 3 pi plus 2e, 3 pi plus 2e will be an eigenvector of the system with an eigenvalue of 3. Often we choose a simple eigenvector like 1, 1 or a normalized eigenvector when we talk about them. To find the other eigenvectors, we have to consider the other eigenvalue. So for lambda equals minus 1, we substitute this into our matrix much in the same way, but now we will get 2, 2, 2, 2, and z is equal to our 0 vector. Expanding out z in the exact same way gives the equation 2x plus 2y equals 0, and therefore x equals minus y. Because of this, we now know that any vector which lies along this line, 1, minus 1, will transform under our application of the matrix to be minus 1 times the original vector. And therefore we have then solved and found all the eigenvalues and eigenvectors of this particular 2 by 2 matrix.